Hello, I welcome you all to this another interesting screencast, and the problem reads the scissors linkage is subjected to a force of P equal to 150 newtons. Determine the angle theta for equilibrium. The spring is unstretched at theta equal to 0 degrees. Neglect the mass of the links. This problem is coming from the Engineering Mechanics Statics textbook, 13th edition by R.C. Hibbeler. We have a scissors linkage, okay, or a frame that is interconnected using the two force members, and they are all pinned at the joints, and we are being asked to find angle theta for equilibrium. This particular problem can be solved directly, of course, just using the equations of equilibrium like we've always been doing. Summation of forces in the x, in the y, and taking moments about any of the points. And we are able to find theta. But it may take maybe a little bit long if we were to use that approach, but would still find the same answer that we can find if we are to apply this particular method that we are introducing, called the principle of virtual work. Right. So what is the principle of virtual work? All this text is coming from the same textbook, Engineering Mechanics Statics textbook, 13th edition by R.C. Hibbeler. The principle of virtual work states that if a body is in equilibrium, then the algebraic sum of the virtual work done by all the forces and couple moments acting on the body is 0 for any virtual displacement of the body. So we are saying the total work del U, okay, which is the total work, okay, which is done on the system due to the forces and couple moments is equal to 0. So let's say we have the total work due to the translational forces F del, let's call del as translational, either in the vertical or horizontal, and let's say del U due to the couple moments M del theta, okay, is another quantity of work done by this. And then if you are to sum up the total work itself, so we are saying the summation of all the forces, the summation of all the forces due to the translational forces plus the summation of all the work due to the couple moments, okay, is equal to 0. Okay, so the summation of the virtual work due to the translational forces and the summation of all the virtual work due to the couple moments is equal to 0. So the method of virtual work is particularly effective for solving equilibrium problems that involve a system of several connected rigid bodies. The method of virtual work is particularly effective for solving equilibrium problems that involve a system of several connected rigid bodies. You can think of this principle of virtual work as synonymous to equations of equilibrium, only that in this particular case, we are using the virtual displacements, and these virtual displacements can either be translational in the y and x, or they can be rotational. And we are saying when these particular vector displacement are parallel or collinear with a force for translational, and for rotational, the angles are also parallel, okay, then you have what we are calling virtual work. And when you sum up this, algebraically sum up all these virtual works due to translational forces as well as due to a couple moments, then the net virtual work that is done on a particular system will be equal to 0. So each of these systems is said to have 1 degree of freedom, since the arrangement of the links can be completely specified using only one coordinate called theta. So we are talking of course, this system here. Okay. So the system that we are going to be focusing on will only have 1 degree of freedom. Okay. So what we are saying is this single coordinate and the length of the members, we can locate the position of the spring force, in this particular case, Fs. We can also locate the position of the force P, okay, using the coordinate theta, okay, and hence it qualifies to be called a single degree of freedom. And this particular virtual work that we are talking about is imaginary displacement. This is imaginary displacement. Okay, it's imaginary. All right, it does not really happen. It's imaginary. Okay, and we are going to be calculating it in our problems as a differential displacement that is given in the positive direction of a positive coordinate. So basically, this is about it on virtual work and virtual displacements. And these virtual displacements can either be a translational in the X or Y, or they can be rotational. Okay. So when you have a force like so, and you have a virtual displacement parallel to the force, then you have what is called a positive virtual work. Okay, positive virtual work. All right. And then if you have a force like so, and you have the virtual displacement in the opposite direction, then you'll have what is called a negative translational virtual work. And then if you have a couple moment like so, and you have the virtual displacement in this same direction, theta, in this same direction, so this is a moment, and then this is the rotational virtual displacement being denoted by the angle theta, then you are going to have also here a positive rotational virtual work, which is just m del theta. But when you have a moment in this direction, and then you have, like I said, both of them have to be parallel, and then you have the angle in the opposite direction, then you are going to have, in this case, a negative rotational virtual work. Okay, is that fine? So we are saying this is going with this is going with this is going with this, and this is going with this. Great. So it's important, these directions, and these are the ones that we are going to be using. Okay, collinear or parallel, if they are collinear and parallel and in the same direction, positive. In the opposite direction, negative. All right, great. So I have an example just below here. I have an example below here that I just want to demonstrate. Let me just get rid of this. There is this beam. Sorry. Okay. All right, let me get rid of this. So we have this beam here, I just want to demonstrate on this simply supported beam and apply the principle of virtual work. So what we are going to do is we are going to release one of the supports, okay, and where you do the release, it really doesn't matter, but for us, we release it at A and leave B fixed the way it is, all right, the way it is connected, hinged here. And we are going to apply a virtual rotational displacement at B, delta theta. So let's apply a rotational at this point here. Let's say we apply, okay, let me exaggerate this a little bit. I just exaggerate it a little bit like so, okay. And then at this point, let me apply del theta like so, okay. And then here I'm going to have this displacement. I'll have these displacements here, but they are all related to the angle del theta, okay. So I'll have this one, okay. I will have also this one, okay. So let's call this one here is, since this whole length here is L, so let's call this as, this distance is going to be equal to L del theta, and then this other one, this height here is going to be equal to half, okay, that's L over 2, okay, del theta. And then now we are saying the total work in a system, okay, is due to these virtual works, when you sum them algebraically, is equal to 0. So let's add them together. Of course, we know that at this point where we have this B here, if I was to draw the free body diagram, I have By, I have Bx, let's demonstrate this virtual application of virtual work on this beam, this simply supported beam. So first and foremost, we have to draw the free body diagram. We have By, we have Bx, and then we have Ay. Once we've done so, then we need to pick our reference point, okay, and that point is going to be fixed, as in it will be fixed, it will not translate, all right, in any directions. It will not translate in the y, it will not translate in the x. So this is our point, this is our reference, and at this particular reference point we are going to apply a rotational displacement, a rotational virtual displacement. So we are applying del theta, okay, del theta. So let's do so. So if we do so, I will just exaggerate it a little bit. If we did so, then I'm saying I'm applying a virtual rotational displacement at this point that we are calling del theta, okay. Then I'm going to have some translational virtual displacement that are related to del theta at the points, because we are interested to identify the translational displacement at the points where we have forces, okay, and these forces can either be applied forces or reaction forces. So this is where the work is going to be done, the virtual work. So this one is going to be equal to L del theta, okay, L del theta, all right, and this one here is equal to L over 2 del theta, all right. Then we know that the total work in a system due to the virtual work, when you've done the algebraic summation, del u is equal to 0. So what we have here, again I said, the displacements have to be parallel to the forces, and these forces can either be applied forces or they can either be reaction forces. So at A, okay, at A, course all these, let me just show one arrow going up, all right, so that we are able to relate. So at A, the displacement is going up and is in the same direction with the reaction force, AY, all right. So at A, we are going to expect AY, okay, because we know that F times del there will be equal to, at A is going to be equal to AY times L del theta, okay. Then at this point, I'm going to call C. At C, F, this is at A. At C, F del is equal to P. P is going down. You've seen P is going down and displacement is going up. Therefore, we expect a negative there. So this is going to be equal to P times L over 2 del theta. Of course, at B, we don't have any movement whatsoever, right? There's no movement in the Y, there's no movement in the X. And we don't have any couple moment applied at B. Therefore, the virtual work at B is equal to 0. So let's add up the two. So this is going to be equal to AY times L del theta minus P L over 2 del theta equal to 0. And if you are to factor out the del theta there, we'll have AY L minus PL over 2, okay, del theta equal to 0. And we know that del theta is not equal to 0, okay, it's not equal to 0. Therefore, our AYL minus P will be equal to 0. And if we made AY subject to the formula, Y and Y cancels there, we realize that AY is just going to be equal to P over 2. And if you look at this, you are reminded of taking the summation of moments about point B, right? If you did that, you still arrive at the same expression, okay? Which is this one, which is equal to 0, okay? If we did so, you will have AY, okay? AY, of course, AY times L, and then you will have P times L over 2 equal to 0. When you look at this, and you look at this, these are the same equations, right? So basically, this virtual work method is just synonymous to applying the equations of equilibrium, only that we are doing it the other way using this particular principle. And this is what we are going to do for this particular scissors structure. Right, let's start doing the work. Let's follow the same steps that we just demonstrated in this structure. So we have this scissor structure. And like we said, the first thing that we do, like I said, you can apply equations of equilibrium directly on this, but it may take a little bit of time, right? Because you'll be forced to start with maybe joint C so that you find the member force in this member force and the other one there, and then move to this joint here, which you can call D. Then afterwards move to A, okay, and once you A there, sum up the equations of equilibrium, then you find theta. So it may take a little bit of time, but you can still solve it. So virtual work method comes in handy. So first things first, look at this support here. This support is free to move in the vertical direction, right? Therefore, we are only going to have a reaction force in this direction, and we denote it like so, okay? We denote this as our Bx. Our A is hinged, or it is pinned at that point, so it's not able to move in the vertical horizontal. So therefore there we have this reaction force, and you also have this reaction force. So this is the free body diagram of this particular system. So now let's choose our reference point. The idea always is to choose a reference point that is fixed. Okay. So let's choose our A, because our A we know is hinged. So this is going to be our reference point. Okay. This is where we're going to refer all the directions, all the distances and so on. So let's call this as our ref point, reference point. Okay. So once we've done this, then now we need to apply a virtual displacement. This virtual displacement we are applying can either be rotational or it can either be translational. Okay. Right. So for us, we are going to choose point C. Okay. Point C is our point where we will apply this virtual displacement, and we'll apply it in the direction of our applied force. But is it okay? Okay, so let's say we apply it in that direction. But is it okay if I applied it in the opposite direction like this? Of course, it's okay. Nothing gets disturbed because the configuration and the displacements and so on won't really get affected. Whatever you're applying here, constraints are still there. And when you come and work on the algebraic sum of the total work in the system, the answer will still remain the same. It doesn't really affect anything. Okay. So we are going to apply it in this direction like so. And then let's call this as our del. We call it as our del C x. Okay, is that fine? Our del cx, or maybe we say del xc, right? Maybe you call it del xc. Okay. So once we do that, then we need to draw a deformed configuration due to this virtual displacement, which is imaginary. All right. So imagine if you were to apply a perturbation in a very, very small virtual displacement in the direction of that particular force, and then this point B is free to move in the vertical direction. So draw a deformed configuration. So you find B will move up somewhere. Let's say B moves to that point. So you're going to expect maybe something like this. Let's say something like this kind of movement. Okay. And then you have this kind of movement like so. Okay. And later on you have this movement like so. And then you have this movement like so. So you have something like this. So imagine that is the new configuration. That is the new configuration. You have these joints there like so. Okay. You have these joints that have moved like so. And this point here. So what happens to C? C has moved. C has changed because this is our new C now, right? C has moved. So we have this this distance here we are calling, this is the actual virtual displacement we are calling del xc. Okay. So once we do so, then everything else changes, right? So then let's find the original distances so that we find this del x by using the first order differential equation or taking the first derivative. So the original distances from the reference point A to C is equal to, we need those ones so that we apply the first order differential equations to find those virtual displacements. So let's call this one Let's call this one as our xc. Okay. Look at the spring, what happens? So when we apply a vector displacement in that distance, the spring gets compressed. So it will have somewhat, it will have some force that will be in this direction like this, right? Do you agree? All right. And then let's call this force here. Let's call this spring force as our Fs. Right. Let's also indicate the position of the original position, so that from there we are able to get the virtual displacement. So this was the original, and let's call this original length is, of course, we are all taking them from our reference point, which is A. So let's call this one as B is YB. Okay, YB. All right. So with that, now let's write the expressions. For YB, what is that length? YB will be equal to, we can just take, so what we have is we have something like this, right? And then we have theta here. Then we have also theta here, right? And then we know the length for these, they are equal. These lengths have been given as 0.3 as well as this one 0.3. So what is the length of this? This is the length we just want to find. So we know to say the length of this is just going to be equal to 2 times 0.3 cos theta, right? Is that fine? Okay, because there's a portion of this and the portion of this that we're adding, all right? So we have a 2 times 0.3 cos theta, which is just equal to, let me rub this, which is equal to 0.6 cos theta. So if we are to take the first derivative of this so that we find our we find our del. Mind you, we have also a del here, right? This distance here, let's say I didn't indicate this distance here. This distance here, let me indicate it in blue. We have also a del there, some virtual displacement. Let me indicate it in blue. From that point there to here, all right, this here, I've exaggerated a little bit. This one here. So this one here is our del. This is our del YB. Okay, is that fine? So now we'll say, taking the derivative, we'll say del YB with respect to del theta is going to be equal to, what is the first derivative when I'm taking cos there? This gives us a minus 0.6 sine theta. And writing this in terms of just del YB, del theta will go the other side, therefore we'll have del YB just equal to minus 0.6 sine del theta. All right. So we've done the first case. Let's do the other case. Right, so what is our Fs? We need to find the spring force. We know that according to Hooke's law, spring force is equal to the spring stiffness K times the change in length. We have already the stiffness given, and I'll convert it to newtons because our P is in newtons. This is 15,000 newtons per meter. Our S, okay, we want to start with the longer length of the spring and subtract it with this change, right? So the longer length is the original, the unstretched, minus the final length. And the original length, we've been told, is equal to this yb, and yb, this one is just equal to 0.6 cos, and the theta we have been told is 0 degrees. So this gives us just a 0.6. L final, we are using the same equation, 0.6 cos, but we don't know the angle. Okay, we don't know the angle at which point equilibrium is going to take place, so we just put theta. So therefore our S is just going to be equal to 0.6 minus 0.6 cos theta. This we can write it as just 0.61 minus cos theta. Great. So we can now move on to apply the virtual work in the whole system. So we know that the total virtual work in the system is equal to 0. And again, the virtual work is just taking place at a point where we have active and reaction forces. So we must have both. We must have a force, we must have a displacement. If any of the two is missing, then you expect virtual work at that particular point to be equal to 0. You need to have both. And we said if they are moving in the same direction, okay, because they must be parallel, but if they're in the same direction, you have positive work. They are parallel. If they are in the opposite direction, then you have negative work. So the only 2 points we are concentrating on is just C and B. So at C we have a P, okay, times the virtual displacement, which is just a del xc, and then plus, I'm putting a plus here, but we need to be mindful of the sign. Maybe I'll put the actual sign. When we go to the other point B, the force, if you've seen the force, the spring is pushing down because it has been compressed, all right? And when the spring is compressed, it will have a lot of potential energy in it, right? So it will tend now to push, okay, converting that energy, all right, into, yes, kinetic, right? So it will tend to push down, this particular point. And because this Fs is pushing down, all right, is pushing down towards joint B, and the virtual displacement initially was going up because they are in the opposite direction. We expect a negative there, right? Negative Fs by del YB, okay, equal to 0. So let's replace this. We have a P of 150 newtons times del C, del xc, or del xc we just found it at 0.9, right? 0.9 sine theta, all right, then minus Fs, we just found Fs as, what was our Fs? We didn't finalize. Okay, let me write the Fs. I thought I wrote it down. All right, let me move this. So our Fs here is just equal to a 15,000 times S, and our S is just equal to times 0.61 minus cos theta. And writing this further on, our Fs is just going to be equal to 15,000 times 0.6. It gives us a 9,001 minus cos theta. So this is the one that is there, so we can write it there as 9,001 minus cos theta, and then times del YB, and del YB is del YB, where is del YB? Is 0.6 sine theta. Okay, sorry, I need to write this. Alright, so after we found the fs, we need to now apply the virtual work principle. Del u equal to 0, that is the total virtual work in the system. It has to be and virtual work is only done when you have two properties. You must have a force and you must have a displacement, or you must have a moment, you must have also a rotational displacement, and the two must be parallel, right? And if they are in the same direction, then you have a positive work. If they are in the opposite direction, then you have negative work. So here we have P, you have P del xc, they are both in the same direction, they are positive. And then at B, you have Fs pushing down, you have the vector displacement going up, therefore in the opposite direction we assign a negative. So Fs del yb equal to 0. Our P is 115. Our del xc is 0.9 cos theta del theta minus our Fs is 9,000, 1 minus cos theta by del yb. Our del yb is 0.6 sine theta del theta equal to 0. We can simplify this further and say 150 by 0.9, 150 by 0.9, it gives us a 135. So we'll have here a 135 cos theta del theta minus, then we have a 9,000 times 0.6. This is 5,000 minus 5,400. 5,400 times 1, then sine theta del theta, and then we have, let me write this down nicely, theta del theta, then you have a plus 5,400 sine theta cos theta del theta equal to 0. Alright, so from this expression we are going to work it out, and from this expression, if we are to simplify it further, we know that our del theta is not equal to 0. Therefore, if we factored out del theta, okay, it's not equal to 0. We can factor out a del theta here. We factor it out. So we factor it out. We just remain with 135 cos theta minus 5,400 sine theta plus 5,400 sine theta cos theta, we close bracket equal to 0. So del theta is not equal to 0, therefore we'll have the inside equal to 0. So we have 135 cos theta minus 5,400 sine theta, then plus what? Plus 5,000 sine theta cos theta equal to 0. Okay, so let's simplify this further. We can simplify this further. Let me divide it by 135 cos theta. If I did that, then I'll have here a 1. I'll have a 1 minus 5,400 divided by 135. Here I'll have a 40 tan theta. Then I'll have plus another 40 sine theta, okay, then equal to 0. So now I have this equation that I need to solve, and we can solve this particular equation using a number of different ways. Among them is the trial and error. So we will use the trial and error method. All right. So we will write this equation as f as a function of theta, which is equal to 1 minus 40 tan theta plus 40 sine theta equal to 0. So we are going to draw up a number line. We'll draw a number line. We have negative and positive. The idea is to find the angle, two angles that will give us, let's say one angle, we call it theta 1, it gives us a negative value. Another angle gives us a positive value. Then we'll know that the solution lies somewhere in between. Somewhere in between. And the range of our theta is from 0 to 180 degrees, because this is how this angle can change from 0 to 180. All right. So this is basically the method. All right. You can check out another video that I did on an example on the trial and error. So we have the range theta from 0 to 180 degrees. So now we are going to draw up a table where we'll be doing the iterations. Okay, we'll draw up a table so that we start doing the iterations. Okay, so there we go, something like this. Hope this is enough. If it doesn't become enough, we'll move on to this stage there. All right, so I think let's move. So we have theta here, we have f of theta, we have theta there, we have f of theta. So let's start. So say let theta be equal to 0. What is our f of theta? F of theta will just be equal to 1, right? So let's try theta equal to, you can go to 20. Let's go to 10 degrees. These are degrees. Let's start. So 1 minus 40 tan 10 degrees plus 40 sine 10 gives us a 0.89. Okay, still positive. Let's go to 20 degrees. 1 minus 40 tan 20 plus 40 sine 20, it gives us a 0.12, still positive. Let's go to 30. 1 minus tan 40 tan 30 plus 40 sine 30. Right, so we have a minus. The moment you have a minus number there and a minus, this is minus 2.09. So you get the minimum values both on the negative and the positive, and then you get the average of the two. So those with minimum values on either side of the number line are the two. Get the average of that, and the average of that is a 25. Plug it back in the function again. 1 minus tan 25, 1 minus 40 tan 25 plus 40 sine 25, we get a minus 0.74. Okay, so again we'll use one with minimum values 20 and 25. We get the average. 20 plus 25, average of that is a 22.5. It's a 22.5. So we keep on doing that. Okay, we keep on doing that. This is one of the methods, but if you have another method, well and good, don't use this one. All right, and then we get again, we plug it in. So we say 1 minus 40 tan 22.5 plus 40 sine 22.5. So you get a minus, we are getting a minus 0.26. all right, again you use the same two values with the minimum values on both sides of the number line. Average of 20 and 22, 20 plus 22.5 divided by 2, we have a 21.25. We plug it in. 1 minus 40 tan 21.25 plus 40 sine 21.25. You have a minus 0.05. Okay, so you keep on doing that. Again, you need to get the average again of the two, because they are the minimums on both sides. So 21.25 plus 20, average of that. So you have a 20. You have a 20 point. You have a 20 point. Let me round off this, 20.63. Okay, you plug in again 1 minus 40 tan 20.63 plus 40 sine 20.63. So you have here a 0.03. So we have two positive values. I mean, this has changed to positive. So again, we get minimum of the two values. So we get this and this. These are the ones that are minimum on both the number lines. We get the average of that. So this is, and then divided by 2. So you will have a 20 there. You have a 20. You have a 20.94. So plug it in. So we'll have 1 minus 40 tan 20.94 plus 40 sine 20.94. So you have a minus 0.01. Right. An error of that kind is good enough. But if you want, you can still proceed. An error of 0.01 is good enough. So an error of, this is good enough. An error of this less than or equal to 0.01. I mean, this is good enough. So you can end here, because you don't have really the time. So you can say theta therefore is approximately equal to a 20.94 degrees. Okay. And you can try it back in the equation. You see it will give us a value of that error, which is not bad. 1 minus 40 tan 20.94 plus 40 sine 20.94. So it's not bad. It's really not bad. So this is a good approximation. This is really a good approximation. So this is about it, and I hope the video was helpful. And if it was, give me a thumbs up, like my video, continue subscribing and liking my channel. Bye bye, and see you in my next screencast.